Here's our setup for investigating Snell's law in the lab. We have this protractor table that's all labeled for you with the incoming ray and the exiting ray and an outline for the piece of plastic we're going to use. This is that piece of plastic. It's lucite and it's semicircular, which is a really convenient shape for investigating Snell's law because the incident ray will always be perpendicular to the curved surface as it rotates, as long as everything's lined up right, which we'll show in a second. So lucite will have a similar proper index of refraction to, you could use this tray to investigate the index of refraction of water, filled up with water. It should be similar. We also have a block of lucite that we could use, and an assortment of other lenses that have more useful shapes in the real world, but are more difficult to determine the index of refraction experimentally and other things. And of course we have the light source. So I'll plug this in. It has a lot of different settings, but I want it to just emit a single ray of light, like so. So I'll line it up at 0 degrees. Let me adjust the camera so you can see what's going on a little better. Okay, and zoom in a little bit. Okay, so I'll put the lucite semi-cylinder lined up in its convenient outline here. Now as I rotate this, the incoming beam, like I had mentioned, should always be perpendicular to this surface of the block. So then we just have to worry about this interface. Whoops, I misaligned it there. This flat interface will be a transition between plastic and air. So we only have to worry about one interface, unlike most lenses, which would have two. But this one's always at 90 degrees. Or here it's called 0 degrees, is the perpendicular to the surface. Okay, that looks pretty good. So when the incident angle is 0 degrees, it comes out at 0 degrees, perpendicular, perpendicular. And I can rotate this to start with 10 degrees. So the incident angle is 10 degrees, and as you can see, it's exiting at, looks to be about 14 degrees. And I'll keep rotating to collect more data points. Of course, we could do any intermediate angle too. It's a continuous sweep, but I'll just move the incident angle to 20 degrees. And you see it comes out at about 30, maybe 30.5 if we're guessing that extra digit. And at 30 degrees incident angle, what does that look like? 48? 48 and a half? And at 40 degrees incident angle, theta 1. Theta 2 looks to be about, now we see an interesting thing where the outcoming light ray, I'm not sure if you can see it on the camera, but in the video here, it looks to be like it's being dispersed a little bit more because the index of refraction depends on the wavelength. Now this is just a normal light bulb, so it's white light, it's a mix of all the colors, and you can see the blue at the top being bent a little bit more than the red at the bottom, if you can see the change in hue of the exiting light ray. Maybe right at the end. And of course you can also see the reflected beam has been getting brighter as we've been increasing the incident angle. So at 40 degrees incident angle, theta 2 is about, getting hard to read because of the spread of the beam. Get it lined up. right about 75. Okay, so I'm going to keep rotating, and pretty much right away the exiting beam has gone past 90. So now we have total internal reflection. And it looks like, I'll try to get it right when it disappears. Looks to be about 42 degrees. And I'll keep rotating. And of course the incoming angle should just be the same as the exiting angle for reflection. Simple off this flat surface and back. All the way to 90. I'll just go straight through. Back to 0 just to check the alignment. And then a good practice would be to check the other side. Since it's symmetrical, you should get the same answers. But it can be a good check to make sure we have everything lined up properly.